Hi everyone, welcome to my YouTube channel. In this video, we're going to discuss on tutorial 22, so topic radioactivity. So we're going to divide into two parts. Part 1, we're going to discuss question 1 to question 4. So before you watch this video, make sure you've done the question given in the PDF link below the video. Okay, question 1. A radioactive sample with a mass of 6.0 times 10 to the power of negative 12 kilogram emits 6.3 times 10 to the power of 7 alpha particles per second. So what is the decay constant of the sample? Given that nuclear number of radioactive sample is 214 and Avogadro's number is 6.02 times 10 to the power of 23 per mole. Okay, so this is mass and this is dN by dt, which is number of alpha particles per second. Then we're going to find decay constant. So symbol used is lambda. So the formula is negative dN by dt equals to lambda n. N is number of the molecules. Okay, for mass Avogadro number, for mass 6.0 times 10 to the power of negative 12. So the number of atoms is n. We don't know yet. So we use the formula, the ratio of mass over molar mass equals to number of molecules over Avogadro number. So we substitute the mass here, and the molar mass is 214 given, and the Avogadro number, and we get the number of atoms. In this case, atoms or molecule lah. We don't know the what kind of the substance given here, radioactive sample given here. So this is number of atoms, 1.688 times 10 to the power of 13. Okay, so we substitute into here lambda n, number of atoms, and then the dN by dt is given, the rate 6.3 times 10 to the power of 7, and we get decay constant 3.73 times 10 to the power of negative 6 per second. Okay, question 2. The isotope radium has a half-life of 1620 years and decays to radon. How long does it take for 80% of a sample of radon, of radium, okay, to decay to radium? This one is radium. Okay, radium 222. This one radium 226. Okay. So half-life for the radium is 1620 years, and the questions one, the time taken for the sample to take 80% to decay. Okay, the formula we are going to use is n equals to n naught e to the power of negative lambda t. So n naught is the initial number of sample that haven't decayed yet. N is the number of sample that haven't decayed yet. So the number of sample that haven't decayed yet, this is 20%, because this one 80% is decayed already. So the number that haven't decayed yet is 20%. So for this formula, make sure you use n is the number of molecules or atom that haven't decayed yet. Okay, the initial number of atoms will be 100%. So for the decay constant is the formula is ln 2 over half-life. So the half-life is given here, and we get decay constant 4.279 times 10 to the power of negative 4. So we substitute into here decay constant. Time taken is the questions once, and n 20% and n naught is 100%. Okay, so we take ln both side. Okay, we use log rule. Okay, then we solve. We get time taken is 3760 years for the 80% of the sample to decay. So just be careful with this n, 20%. N represent the number of sample that haven't decayed yet. Okay, now we go to question 3. Okay, before we go to question 3, there is another method to solve this problem. Okay, the second method is we know that initial number is 100, let's say 100%, it's the number of the atoms. Then to become half of the 100%, that's mean 50%, the time taken is half-life, okay, half-life, and the number of the atoms becomes half. Okay, the number of atoms become half. Uh, the time taken is half-life. Then continue after 50%, it becomes half, 25%. So this is another half-life for the for the becomes half, for the number of atoms become half from the initial here, 50% to 25%, which is one. If we continue the pattern here, we can see it's become 1/4 of initial, and so on. So we can see that there is a pattern here. So from this pattern, every time the number becomes one half-life, and then two half-life, three half-life, and continue. Okay, so the pattern here, 1/2, 1/4, so we can write as 1/2 to the power of x of the initial number of atoms. Okay, and then this x is same as the number of half-life. Okay, each time it decreases to 0.5% or half of the number. So 1/2, 2/2, and 3/2. So this is the pattern, x times half-life. So we can combine this formula. So combine this formula. So the time taken will be, we cross multiply here. Okay, the time taken, this is continue, the time taken here, half-life, two half-life, and three half-life. So this is the time taken equals to x to the power of half-life, and this will be number of atoms remain, okay, that has not decayed yet. So n equals to 1/2 to the power of x times number of atoms. So from the pattern here, we form the equation. So you can memorize this new equation. So if in the exam you forgot the previous formula that we solved just now in the previous slide, so you can use this formula instead. Okay, so now we can substitute the into the equation here, the given information. So n is the number of atoms that haven't decayed yet, which is 20%. So 20/100 n naught of the initial equals to 1/2 to the power of x n naught. Okay, we can cancel the n naught and we get 2 to the power of x equals to 5. And take ln both sides, so we can solve for x. X is 2.32, and this x we can substitute into the this formula. So 2.32 equals to t over half-life, which is 1,620 years, and we get the time taken 3,760 years. So we get the same answer as the previous solution. Okay. Okay, now we go to question 3. The activity of a sample of polonium-210 is 152 becquerel. The half-life of polonium-210 is 138 days. So what is the decay constant of polonium-210? So we do question A first. So for question A, the question's one decay constant, so we can use formula ln 2 over half-life. So we substitute the half-life given here, 138 days, and convert to second. So 138 times 24 hours. So 24 hours times 60 minutes and times 60 seconds. So we get the unit for half-life here in second. So the decay constant is 5.81 times 10 to the power of -8 per second. Okay, next, we are going to do B. Calculate the number of polonium-210 atoms in the sample. So we can use formula dn by dt equals to negative lambda n. So dn by dt is given 152. Okay, the rate okay, here the rate in becquerel unit. So this is the activity, so which is dn by dt, so 152 equals to lambda decay constant and times the n. So we just want to find the rate. Here is negative, negative cancel out already, so become positive. So the n is 2.6 times 10 to the power of 9. Okay, so that's the number of polonium 210 atoms in the sample. This is the number of atoms that haven't decayed yet. Okay, next questions are C. Question C, how long does it take for the activity to decrease to 50 becquerel? So initial is 152 becquerel, then becomes 50 becquerel. Okay, so we use this formula, n equals to n naught e to the power of negative lambda t. And we know that n is also can replace by activity. So n is directly proportional to activity, so we can use this n, we can substitute with the activity. And initial n is the activity given here to decrease to 50 becquerel. So substitute into here, and initial activity is 152 becquerel. So e to the power of negative lambda is the decay constant and times t. So we bring 152 to the left side. Okay, then we can use log rule. So take log both sides. Okay, now we solve. We get time equals to 1.9137 times 10 to the power of 7 second. Okay, so that's the answer. And we can convert to days. Is equals to 221 days. Okay, convert second to days. Because the half-life given here in days, so you can convert to days. Okay, next we can use another method. Okay, another method instead of using the n equals to n naught e of negative lambda t. So we can use the similar to the question 2, another method. So the half-life each time the activity become half, okay, is given by this half-life, and then another two half. The second one is two half-life, continue two half-life, so it reduced to half of the initial this initial. So 1 per 2 times 1 per 2 a naught will be 1 per 4, and this pattern will continue. So we get the pattern as 1 over 2 to the power of x initial activity, and the time taken will be number 1 to 3 here, number of the same pattern here, above pattern, so x times half-life. Okay, then this is the time taken, x times half-life, and we get x equals to t to the power of half-life. And this x okay, this x is can be substituted into here, and the activity become 1 over 2 to the power of x a naught every time. Okay, then we use this formula instead. So a is the activity given here, 50 becquerel, and 1 over 2 to the power of x times initial activity given 152 becquerel. Okay, so cross multiply, we get and take ln both sides, and we get x 1.6041. And to find the time taken, so we substitute into the equation here. The x is 1.6041 equals to t over half-life. So half-life is 138 days, and we get time taken 221 days. Okay, so we get same answer as the previous method. Okay, lastly, question D. How many atoms of polonium-210 remain in the sample when the activity is 50 becquerel? So next we are going to find number of atoms. Okay, we can use formula dn by dt equals to negative lambda n. So dn by dt is the activity give 50 becquerel. Okay, and the n is directly proportional to the activity, so that means we can use this 50 becquerel unit. So dn by dt we can use 50, and the decay constant in question A just now we got 5.81 times 10 to the power of negative 8, and we get number of atoms remain, which is 8.6 times 10 to the power of 9. Okay, and the last question for part 1. A sample initial contains 1.0 times 10 to the power of 8 nuclei of a radioactive isotope of half-life T half subscript half. Estimate the number of nuclei remaining after a time equal to 0.8 half-life. Okay, so you can use this formula. Two formula can be used. So if we use this formula, n equals to n naught e to the power of negative lambda t. Okay, so the n naught is 1.0 times 10 to the power of 8. So this is number of nuclei, initial number of nuclei. Then the lambda we can use formula ln 2 over half-life, and the t is given here 0.8 half-life. So this half-life can be cancelled out, so becomes ln 2 cancel out, so ln 2 times 0.8. So the we get the answer 5.74 times 10 to the power of 7. Okay, so you can solve using log rule. So I didn't show here. I hope you all can do. The answer is 5.74 times 10 to the power of 7. So second method, you can use this pattern. Okay, so we get the pattern n equals to 1 over 2 to the power of x n naught, and the time taken is x times half-life. Okay, now we can but this time the questions given, the questions wants number this number of atoms remain, so that means we use backward. We find x first. X equals to 0.8 half over half-life. Okay, the time taken given here, then we can cancel half, we get x 0.8, then we can substitute into the above equation. So 1 over 2 to the power of 0.8. So initial sample contain 1.0 times 10 to the power of 8 nuclei, and we get the answer 5.74 times 10 to the power of 7. So same answer as if we use this formula. Okay, so that's all for part 1. Okay, we continue tutorial 22, part 2, topic radioactivity. So the question that we are going to discuss is from question 5 to question 8. Okay, question 5. In a nuclear reactor, the isotope natrium is produced at a constant rate R from the stable isotope natrium-23. So write an equation relating delta N, the small increase in the number of natrium-24 atoms in time delta T in terms of lambda. So the decay constant of natrium-24 and R, the rate of production natrium-24. And question B, hence show that the number of natrium-24 atoms present in the reactor will eventually reach a constant value. Okay, question A. So we use formula dn by dt equals to negative lambda n, and dn equals to negative lambda n dt. Okay, so this dn is the number of atoms that haven't decayed yet in time here delta t. Okay, but the question the given r is dn by dt. So for the dn prime, okay, what that we are going to find is equals to cross multiply r r times dt. So this one we don't know yet. Uh, this is the number of atoms produced in time dt. Okay, so this one is not n. This n and this n is not the same. So this is given produce. So r is dn by dt. So to see the difference between these two n's, so we use n prime instead to represent the number of atoms produced in time dt. So make sure you can see the difference between this n. Okay, so you can imagine like this. Let's say this is the n number of atoms that haven't decayed yet. Okay, when the number of atoms decayed, so it decrease in number. Let's say it decreased by dn. So this is the remain. Okay, and this is the decreasing that is produced and prime number of atoms that produce, but the total overall number of atoms will be the same. Okay, and then as the time increasing, so the number of atoms decays increasing, but the number of atoms remains decreasing. So you can see that the patterns. Remember that n prime represent the number of atom produced or decayed. So n is the number of atoms that haven't decayed yet. So you can see the difference between these two, but total of the number of atoms remain the same. Okay, so the delta n here, this is the small increase. So the small increase of the number will be negative lambda n delta t. So this one negative lambda n delta t plus the r delta t. So using these two formula, but the question asks to use this symbol. So you just follow what's the questions wants. So the n here will be delta n equals to negative lambda n delta t plus r delta t. Okay, so delta n equals to, so we factor out delta t, so bracket r minus lambda n. Okay, so that's the answer for A. The question asks to write in terms of delta t, lambda and also r. So the question asked to answer in this form. So this is the answer. Okay, now we go to question B. Then show that the number natrium atoms present in the reactor will eventually reach a constant value. Okay, so now from this one, when delta n approaching 0, so we use the derivation rule. Okay, so it's become dn equals to r minus lambda n bracket close bracket here, delta t becomes dt. So if this one approaching 0, so we use dn. Okay, so now we bring r minus lambda n, the whole bracket here, to the left, and then we use integration rule. Integrate, take the integral both side like this, and the number from initial number of atoms 0 to n that haven't decayed yet, so 0 to n, and then the time taken 0 to t. Okay, so we separate the variables. In other words, we separate the variables here. So the right side is the variable is t, and the left side the variable is n. R is a constant. Okay, so we continue to the left side of the slide. Okay, so the integral of this one, we get ln r minus lambda n over negative lambda. So we use log rule. Okay, log rule. So for the n here, the coefficient is negative lambda. So we divide by negative lambda. Okay, lambda is decay constant. Okay, on the right side, the integral will become t from time t to 0. Right, left side n to 0. Okay, so now we substitute n into the equation here. Okay, so on the right side becomes t, because t minus 0 is t. But on the left side, so when you substitute n here, so what you get? Okay, lambda is a constant here. We can um, factor out negative 1 over lambda. So the bracket becomes ln, okay, r minus lambda n, and minus ln r minus lambda 0, because 0 here we substitute into n here, right? So we get lambda times 0. So we use integration rule, right? We use integration rule. Okay, now we solve. We get ln r minus lambda times 0, so r minus 0, so we get ln r. So this one remain the same. And cross multiply lambda, so we get negative lambda t. Okay, now we use log rule. Okay, minus, this is log rule, we becomes ln r minus lambda n over r, because minus, so we divide by r. Okay, then we convert to index index rule. So log rule to the index term. So ln is log base e, so becomes e to the power of negative lambda t. Okay, so now we continue to simplify this. Okay, 1 minus lambda n over r. Okay, simplify this. R over r is 1, so minus lambda n over r, and lambda n over r bring to the right side become positive, and e to the power of negative lambda t bring to the left side become minus. Okay, continue, and we get n. Lambda over r bring to the right side becomes r over lambda. Okay, so when this t approaching infinity, so when the times goes on, okay, so this is what the questions want, eventually reach a constant value. So that's mean when the time to reach infinity, so the e to the power of negative lambda t will approaching 0. So this one will approaching 0. So we get n equals to r over lambda, because 1 minus 0 is 1. So r is a constant and lambda is a constant. So that's mean it is proven or shown that the number of natrium-24 atoms present in the reactor will eventually reach a constant value. So r is constant, lambda is constant. So proven, shown. Okay, next we go to question 6. Okay, question 6. The activity per unit of atmospheric carbon due to the presence of carbon-14 average about 0.245 becquerel per gram of carbon before 1900. Find the fraction of carbon atoms that were carbon-14. So we do question A first. We from the formula n equals to n naught e to the power of negative lambda t. So the lambda decay constant is ln 2 over half-life. So the half-life given in years, 5,730 years. So we convert to second, because here given 1 year in second. So 1 year in second is 3.156 times 10 to the power of 7 second. So convert to second. So we get decay constant 3.83 times 10 to the power of negative 12 per second. So if we use this formula, so if you use activity 0.245 becquerel into here, the problems is we don't know t. T is not given, so we cannot use this formula. So we use another formula for activity dn by dt. So dn by dt equals to negative lambda n. So we can find n, because the questions want fraction. So we need to find n over n1 over n2 lah. N2 will be the total number for 1 gram. So n will be the number of atoms if we using this activity 0.245 becquerel. Okay, so remember that the question got per gram here. So for just 0.245 becquerel, so we substitute into the equation here, 0.245 becquerel. So the decay constant, okay, calculated just now is 3.83 times 10 to the power of negative 12. So the number of number of atoms that haven't decayed yet is 6.40 times 10 to the power of 10. So this is for activity 0.245 becquerel. But we have 1 gram here, given this is 1 gram. So for 1 gram, the number of atoms will be larger in value. So let's calculate them using this formula. The ratio of m to molar mass equals to number of molecules for this 1 gram over Avogadro number. So for this 1 gram here, over molar mass given in the question 12.011 equals to the n prime prime. So just to state the difference between these two n, okay, for 1 gram will be n prime prime. So we use this symbol. So Avogadro number 6.02 times 10 to the power of 23. So we get the number of atoms for 1 gram is 5.01 times 10 to the power of 22. Okay, so now we can get the fraction. So the fraction is this one, 6.40 times 10 to the power of 10 over 5.01 times 10 to the power of 22. So the answer is 1.28 times 10 to the power of negative 12. So this is answer for 6A. Okay, next we go to 6B. In analyzing an archaeology specimen containing 600 mg of carbon, there are 192 decays in 1 hour. What is the age of a specimen, assuming that its activity per unit mass of carbon when it died was the average value of the air? Okay, so question B. So this is activity given 192 decays in 1 hour. So we can use formula A equals to A naught E to the power of negative lambda T. Okay, for 0.45 becquerel, this is for 1 gram. So for the 600 milligram carbon, so that's mean what is the activity? Okay, so we use the ratio, okay, for 600 milligram. So 0.245 over A naught. So 1 over 600 convert to gram. Same unit, must be in same unit. So we get A naught 0.147 per second. Okay, so this is per second because becquerel is per second. Okay, SI unit. So we substitute into here. Okay, so to substitute into here, we need to use 192 decays in 1 hour. So we convert to hour first. So this one is in second. So we convert to hour because we are going to make use of 192 decays in 1 hour later. So we convert 0.147 per second. So convert to hour become times 60 minute times 60 second. So we get 529.2 per hour. Okay, so done. Next is the gamma, the lambda. Okay, decay constant. We also calculate here ln 2 over half life. So we get 1.2097 times 10 to the power of negative 4 per year. So be careful with all the units given. Year, then here given hour. So this one is per year. Okay, so we substitute into here. A activity given 192 decays in 1 hour. Okay, this one is per hour. So this activity, initial activity, we calculate already per hour. 529.2 per hour. Okay, next, the negative lambda T here. So the negative lambda here, decay constant is this one. This one is per year. So that's mean the time taken here also will be in year. So this hour, the activity here we cancel out already. So our final answer for time is in year unit. Okay, so now we bring 192, okay, to the right side, become over 192, and this one bring to the left side, become positive. So e to the power of positive 1.2097 times 10 to the power of negative 4t. Okay, Then we use log rule, take log both side. Okay, then same base, ln is log base E, so same base, so it becomes 1 point, use log rule, so it becomes 1.2097 times 10 to the power of negative 4 times T. Okay, so this one is 1.0138. So before we come to final answer, you can use straight away calculator without stopping at this step. Okay, so the answer is 8,381 years. So the unit is years because just now our for activity cancelled out already. So be careful with the unit you use in the to answer the question. Okay, so the unit is years, 8,381 years. So this is the answer. Okay, now we go to question 7. Measurements indicate that 26.59% of all rubidium atoms currently on the Earth are the radioactive rubidium-87 isotope. So the half-life of rubidium-87 is 4.75 times 10 to the power of 10 years. Assuming that no rubidium atoms have been formed since, what percentage of rubidium atoms were rubidium-87 when our solar system was formed 4.6 times 10 to the power of 9 years ago? Okay, so we are going to use formula n equals to n naught e to the power of negative lambda t. Okay, so what percentage rubidium atoms were rubidium-87? So this is what we are going to find. So we use in the percentage unit. So n 26.59 percentage. This is the presence percentage. 26.59 percentage. So we are going to find at 4.6 times 10 of 9 years ago. So what is the percentage? This is considered as initial percentage. E to the power of negative lambda, and then time taken is 4.6 times to the 10 of 9 ago. So time taken. So decay constant, you can use formula ln 2 over half-life. So half-life is given 4.75 times 10 to the power of 10. Okay, so we get the answer here. This is decay constant per years because the given here is half-life in years. Okay, so now we substitute into the equation. Okay, so we solve for this percentage of rubidium-87. So we get 28.4%. Okay. So this one remain on the right side, and we bring this to the left side. Okay, and you solve, you get a percentage of rubidium 28.4%. Okay, next we can use this method also. Okay, instead of using n equals to n naught e to the power of negative lambda t. So you do backward, find the x first, time taken is given, and then half-life is given. Okay, so we get x, and we substitute into the equation above. So 26.59% is the presence percentage, 1 over 2 to the x. So you substitute this x into here, so we get the initial n. So we cross multiply, so we get same answer as the previous method, 28.4%. Okay. Question 8. In a radiotherapy treatment, a patient is exposed to a radioisotope with a half-life of 5 days and an initial activity of 3.82 times 10 to the power of 6 becquerel for 5 minutes. So the same treatment using the same radioisotope is given 8 days later. How long the patient must be exposed to the radiation in order to receive the same dosage? So we use formula n equals to n naught e to the power of negative lambda t. So the n can be replaced by activity. Okay, so the activity given here is 3.82 times 10 to the power of 6 becquerel. So for 5 minutes, so we substitute the time taken here 5 minutes, and the decay constant is using formula ln 2 over half-life. So half-life is 5 days, convert to minute. So 5 times 24 times 60. So we get decay constant 9.6270 times 10 to the power of negative 5 per minute. So you substitute into here and you get the activity is the same, 3.82 times 10 to the power of 6 becquerel. So why it is the same? Because 5 minutes compared to 5 days, so this is a very short time. So nothing changed for it still have the same activity. So 5 minutes is small compared to the half-life of 5 days. So the activity of the source can be taken to constant value here. Okay, so now if so now we calculate the activity after 5 days. So the activity after 5 days, and we expose it for 5 minutes. So what happened to the activity? Okay, if 3.82 times 10 to the 6 initial initial uh, initial activity, okay, initial activity here 3.82 times 10 to the 6 e to the power of negative decay constant times the 5 days. Okay, this half-life after 5 days. So we expose it the same for 5 minutes. Okay, the question state here for 5 minutes. So we get activity equals to 1.9100 times 10 to the power of 6 becquerel. Okay, now after 8 days, what happened? The question asks for how long patient must be exposed to the radiation in order to receive the same dosage. So for the same dosage, how long it will be exposed this radioactive to be exposed to the patient, okay, for how long for the same dosage. Okay, so for 8 days we use we calculate the new activity. So initial will be 1.9100 times 10 to the power of 6. So we continue using the same radioisotope. Okay, mentioned in the question here, the same radioisotope. That's why we use this activity, initial activity. So e to the power of negative decay constant, and the time taken is 8 days later. Okay, 8 days later. So we get the activity is 6.3007 times 10 to the power of 5 becquerel. So this is activity at 8 days later. Okay, at 8 days later. Okay, so to find the time to expose to the patient, so we can take the ratio. Okay, we can use the ratio. So just now 1.9100 times 10 to the power of 6 becquerel. So this is exposed for 5 minutes. Okay, for to the patient 5 minutes. So if 6.3007 times 10 to the power of 5 becquerel, so how long will we expose so that we get a same dosage? Okay, so using ratio, but this time we need to use inverse because the time will be increased. We need to expose for longer time so that to get the same dosage. Okay, so we use opposite inverse ratio. So T equals to 5 times 5 times 1, 5 times 1.9100 times 10 to the 5 over 6.3007 times 10 to the 5. So we get the time taken 15.2 minutes. So that's the answer. Okay? So if you don't use inverse ratio, so you will get the time shorter, so which is not possible. So you should take the inverse ratio. So it is logic to be time taken longer for the exposure here. Okay, we can use another method. So we can use this method, okay, using the formula here, n equals to 1 over 2 to the power of x n naught, and x equals to t over half-life. Okay, using the pattern, this pattern, half-life pattern. Okay, so now using this formula, a equals to 1 over 2 to the power of x n naught. So you substitute X is T over half life. So T is 5 over 5 minutes over 5 days convert to minute. Okay, so we get 3.82 times 10 to the 6. So we get same answer because 5 minutes compared to 5 days. So it's too short. So that's why we get same answer here. So the mathematics logic uh, is there. Okay, you can see that the activity will remain the same. Okay, now we can calculate 5 days later. So what happened? Exposed for 5 minutes. So the activity becomes here we can substitute the time taken 5 days later. Okay, divided by half life. So the same half life 5 days later. So this one is 2 to the power of 1 times the initial activity 3.82 times 10 to the power of 6. This one is just now exposed for 5 minutes. So this A1 also exposed for 5 minutes. So we get 1.9100 times 10 to the power of 6 becquerel. Okay, so now it start to change. The activity start to change if exposed 5 minutes at 5 days later. Okay, so for the 8 days, okay, that use a symbol A2 for 8 days, the activity become, okay, the X here is T time taken 8 days, convert to minute, and then divided by half life, here half life in minute. Okay, and then the initial activity will be 1.9110 times 10 to the 6 because the question said continue using the same radioisotope. So we use the same radioisotope. So that's why we use N note here 1.9100 times 10 to the power of 6. So the answer, the activity becomes 6.3007 times 10 to the power of 5 becquerel. Okay, so to find the time taken, okay, to expose the radioisotope, so 5 minutes taken for this activity. Then for the 6.3007 times 10 to the 5 becquerel, so how long it represent with this T symbol to be exposed to the patient. So we cross multiply. This one we use an inverse ratio because this is time taken. Same reason as previous slide. So 5 times 1.9100 times 10 to the 5 over 6.3007 times 10 to the power of 5. So we get 15.2 minutes. Okay, so the same answer as the previous slide. Okay, so now that's all for tutorial 20 and